Afternoon. Sorry, losing my voice. For those of you, I see some familiar faces in the group. For those of you that are expecting me to present my normal TPN pen presentation, don't run away. This is new. We want to introduce an open flow controller that we've been building over the last 6 or 7 months. We started out as one of those skunk work projects that Caroline mentioned at the beginning, where we were trying to solve some specific things. Within Telstra, it was easier for us to kind of go off in a corner and do some things on our own. And we kind of came up with this solution. We are releasing this back as open source, so this is available as of today. I'll give you the GitHub repositories at the end. And we're doing that so that we can take input back from the community. The solution that we've developed solves our specific needs, but we know we're missing things, and we really would like to build a community around this and understand how we can advance it across the entire community. So if I was sitting in your shoes, I'd be asking myself, why are they creating another controller? There's literally a million controllers, I think, out there. If I missed yours on this slide, please accept my apologies. We were just trying to come up with a list of some of the controllers that are out there. We've tested a few of these, the major ones that you would expect. We haven't tested all of the ones that are out there. But with every single one of them, we ran into some challenges that we were trying to solve that they didn't support. So within the organization, when we said we were going to do this, we got called crazy and a few other things that I won't repeat, and kind of decided we'd take it on anyways and try to create a solution that, kind of scaled and met the requirements that we were looking for. If I had to do it again, well, let's just say I had hair before we started this exercise. So if I had to do it again, I think we would think a little bit harder about using one of the major controllers. So marketing paid for me to be here, so I have to do a marketing slide. I promise this is the only one where I'm going to mention a product that we have in the network. But I think it's important to understand where we came from and what we were trying to solve. Within Telstra, we have a product called the Telstra Programmable Networks, and it is the newest version of what under PACnet we called PEN. And the idea was to provide a user experience to the customer to consume network services the same way they buy compute and storage and everything else in their networks or in their overall IT infrastructure. And the way they were buying it was on demand, and they were still having to buy network services and fixed 3-year contracts with with point A and point Z predetermined and difficult to make changes to it. So we set out to solve that problem and offer bandwidth on demand as the initial release. And we took it one step further, and we kind of made the decision that our customers are smarter than us. And what they really wanted was the ability to take a bunch of different building blocks and glue those building blocks together, stick those building blocks together to build the network that they actually want to consume. This is the actual GUI. It shows a real customer network. And it kind of shows some of the major building blocks that we've deployed across this network. So we have this integrated into our IPVPN. We have it integrated into our internet product offerings. We have virtual routers, virtual firewalls, so an NFV component that sits inside the network. And then we can combine actual ports, top-of-rack switch ports that are connected in our data centers in a customer's rack directly into this overall network. Give you an idea, if you were trying to build that network today, call your vendor, I'll pick on Telstra, call Telstra, go from the initial phone call till the time it gets delivered, and that network kind of spans between the UK, Sydney, and in Japan, you're probably looking at 6 months. We built that in a presentation I was giving yesterday, and I think in about 10 minutes, completely up and operational and functional. And this is all built on OpenFlow, which led us to building our controller. So why did we have to go build our own controller? We thought we had a unique problem. I'm not sure it was unique, but for us it was somewhat unique. The network on the left is the actual controller. It's not a constellation. It kind of looks kind of funky at the moment. But it is the true network that we have in production at this moment. And the network spans, I think, 35 POPs, 10 countries. It goes from Europe through the US, throughout North and South Asia, and Australia, and ends in the Middle East. So kind of a global network. And our controller sits in Hong Kong. Now, a controller sitting in Hong Kong trying to manage servers that are in London means we have 300 milliseconds of latency in the control plane. We have to bounce those control planes through various NNIs with local partners, which means our stability of the control plane is kind of in question at some times. So we start to see weird things happen. We start to see switches drop that shouldn't actually drop. The second problem we run into with this network is it's an overlay network. So it's got lit services, dark fiber services, got pretty much everything in the core of the network. A standard method we saw in most of the controllers that we were using, and the first one that we deployed on, it only relied on the link state of a port to determine if a ISL, interswitch link, was up or down. But since some of these lit services aren't passing link state, those services are always up, those ports are always up, even if we can't get traffic end to end, which was giving us false positives and causing pain for our customers. So we were looking at ways that we could solve the stability problems as well as the definition of what the current state of the network is. We wanted a lot. We set out with a pretty ambitious goal across what we wanted to do in this network. We kind of broke it up into a few main categories, and the first being the real definition of the network. What does the network actually look like? How do we know what's working, what's not working? How do we deal with the latency and the instabilities we were seeing in our control plane? And how do we get scale, horizontal scale in the network? As we added more and more switches, as we add new POPs, the complexity of the network increases exponentially. And trying to do path recon calculations and understand the real state of the network has become a real challenge for us. We kind of broke down the problems that we found in the existing controller base in kind of three major buckets, the first being convergence. So what tools do we have in order to get the real definition of what the network looks like? Again, remember, we can't rely on control plane because it's somewhat iffy in some markets. We can't rely on port states because we could have a combination of lit services and unlit services at the underlying core. And we really struggled with executing path recomputation events, so moving a customer's traffic when we really didn't need to move that customer's traffic. Typical use case, or typical example, switch would report that it was offline because the control plane took a hit, but the flows that were transiting that are still increasing counters on both sides. So we know that that switch is not really offline, we just can't reach it, but controller would say it's offline and move all the flows that were going through that switch onto another path. Introduces a hit to the customer and doesn't make a great experience. So we looked at, how can we deal with this? And we looked at doing an event processing system. How can we take in lots of different events and correlate those events to create a solution that gives us a better overall view of the underlying network? The last challenge we saw was our network's WAN-based. And if you look at most of the controllers, at least when we started this, and this product's been live since 2013, so we're going on our 4th year. It was launched almost 4 years ago exactly. So we were doing this back in the early days of OpenFlow and the early days of controllers, and they were all, for the most part, built for the LAN. And we were putting this into a WAN with, very high latency and a highly distributed network that just didn't scale. So how did we solve this problem? We broke it into a tiered structure. And we first started off looking at how do we deal with the control plane issues, how do we deal with scalability at the switch level, and how do we deal with stability within that communication path between the switches and their controller. So we introduced a concept that we call an OpenFlow speaker. And the OpenFlow speaker's main job is to take OpenFlow messages that it receives from the switch, convert them into our messaging format, and pass them upstream. And because we can attach a switch to multiple speakers, we now have a way to add redundancy at the actual OpenFlow level or at the controller level. The switch sees it as a controller. The speakers are listening to a queue, so we can have multiple speakers listening to the same queue, and it's constructed in such a way that they don't step on each other. So we kind of get that horizontal scale, we get the redundancy built in there, and we can regionalize it. So we can decide to have a single controller or single speaker doing the whole world, or we can put them all the way down into the POPs if we want to, or do regional-based solution to get rid of that latency issue and that control plane stability issue. We went with Floodlight, as you can see there. It was a great way for us to get started with that speaker. With the OpenFlow protocol, we liked the fact that it was based off LoxyGen. Switch vendors didn't like it because they don't fully conform to the standard, and LoxyGen will catch them up every time. But Floodlight was a very quick way for us to get started with this. We then move in kind of into our message queue, and forgive the graphics. It was a very long flight from Australia, and I was bored. So we then moved into the message queue that we wanted to put in the middle of this, and we chose Apache Kafka. And we chose Kafka because it scales nice horizontally. It's backed by HDFS. It has a concept of a consumer group, so we can have multiple of those speakers attached to the same topic, and it guarantees that only one consumer is taking off of them, or taking the messages out of the queue. But it also lets us replay it. So if we do have a catastrophic event and we lose communication from the speaker back to the Kafka queue, we can just replay when we attach and catch up to where we're going across the board. We're also using it in other parts of the network, or the other parts of TPN, so it's a logical choice. The heart of the network is what we call the correlation engine. Don't ever let engineers pick names, because we come up with crappy ones. But we use Apache Storm for this, and this is probably the most controversial decision we made across the network, which is why Storm. If you're familiar with this space, event stream processing space, Storm, I think, is a great solution. It's a little old. It's still being developed actively, but newer solutions like Spark and some of the things from Google seem to be leading in this battle. I had used Storm for a different project, so it was just kind of a natural fit for us. The concept with Storm is that we have, this isn't a presentation on Storm, but we have spouts that inject data into a Storm topology. Think of it as a bunch of lambdas, if you will, inside Storm. And then they get processed. And in each one of those, we can turn up more and more processors, so we can scale at the individual function level across the core of the network. It means that we can process in real time. It means we can drain that Kafka queue in real time. Right now, we push 2 million messages a second through this network. We can process that queue rather quickly. We don't have big delays. We're sub-second, 20, 30 milliseconds actually for processing through Storm. And it's very easy for us to add new functionality because we have a template for our Storm topologies, and it's very quickly to add features to it. The only problem is it is Java, and most of my developers are Python, so we had a bit of a learning curve to get from Python into Java for them. We needed a backing store. We don't really keep state anywhere. There's a little bit of state that we have sitting in the Storm topologies, but our single source of truth, well, actually we have two, but the main source of truth is the switch itself. So if the whole system goes down completely, we'll interrogate the switch and rebuild the view of the network up from what's based on the switch, and then audit that against the OSS systems and BSS systems to make sure that we have in production what the customers actually asked for. That allows us to deal with that scale problem rather easily because we don't have to maintain state between each of the individual components in the system. We wanted a GraphDB. We went with Neo4j as our GraphDB. It provides us the shortest path functionality as well as a fairly robust graphing database on the back end. We've put some topology calculation engines in front of that. And then the last piece that we needed is some way to store all the stats and data that we were taking back. We take back data points anywhere from every 500 milliseconds all the way up to a couple of seconds across the network. We do this across the every switch, so every port, and every flow and every ISO. We do active and passive monitoring across the network. So we take back a lot of data. OpenTSDB was a rather easy choice for us. We were using it in other solutions, but it's also an extremely quick solution in order to bring back time series. So just re-looking at this from kind of a block diagram or a bottom-up view of what the overall infrastructure looks like. We have a northbound interface, which is how you inject commands into the overall system. It's built on top of HDFS, or then in the core you have HDFS. HDFS is a great file system that automatically replicates. Think of it as a 1+3 kind of model. So every time we write to it, we replicate it 3 or 4 times. We use Kafka, as I mentioned, and HBase sits behind OpenTSDB as the data store for OpenTSDB. They write to HDFS, so we automatically get that redundancy across there. Zookeeper kind of feels like my job sometimes in my team. But Zookeeper is managing all of the individual components, so Storm and TSDB and Kafka and HBase and HDFS, they all know where to talk to. It's kind of a traffic cop. We have our topology engine that we wrote ourselves, the last piece of Python actually still inside of it, and it's responsible for actually programming the end-to-end network. One thing that's unique about TPN is it's not a tunneled solution. We don't pre-create tunnels across the entire network and color packets and shove them into there. We do that actually on a flow-by-flow basis, and we do that on a hop-by-hop basis across the core of the network. That was to give us a little more flexibility and be able to monetize the core of the network slightly different. There's a lot of subsea capacity in there, and there's low latent paths and high latent paths. And then on the far side of that, you kind of have the open flow switches that are pushing out, that are actually taking the commands and making sure the forwarding works. Promised the last diagram on the overall sequence that we have, but kind of a rough sequence diagram. That may or may not be easy to read, but the general idea is on the left-hand side, the open flow switches, they're sending messages through Kafka into Storm. Storm's grabbing those messages and processing them and making decisions on those. And the main thing we're trying to do is take multiple data points to determine if we had a topology change. Don't just look that a switch dropped. Look at the actual flows going through that switch on their ingress and egress switch and see if if their counters are still increasing, so we're still pushing traffic. Do active monitoring of every single ISL and every single flow we have through the network, where we inject the packet, run it through the network, pop it out, and measure end-to-end latency across the network. Once Storm kind of figures out there needs to be a change to the network, it goes off and talks to Neo4j, and the topology engine figures out all of the switches that need to be touched. And then the process just reverses, goes back through Kafka. Kafka goes back out to the speakers, and the speakers go back out to the switch. We've been debating the best solution for topics. So in Kafka, topic equals a queue. So do we do per switch topics? Do we do topics per region? Do we do topics as a single global? We've tried every single combination. There's 6 of us on the team, and we have 30 different answers to the best solution on that. I suspect we'll never get a real answer on the best way to do that. So where are we at today? It works. It's going into our production network. It will be replacing the current controller, which is a commercial controller, probably, knock on wood, the end of this month, if not early November. It lets us create, modify, delete flows, push pop, modify the VLANs. TPN is based off a E-line service at the moment, and that's a limitation of the original controller. We get the telemetry data back. We're able to make decisions based off that telemetry data that we're getting back. And it has all the operational things you would expect in a traditional controller. It's auto-discovery of its network, gives you alerts and all those kinds of things. The beauty of Kafka is that anything can listen to a Kafka queue and make a decision. So as we have to add the operational tools, it's very easy for us to just write a simple listener to a specific queue, and they can start to act on individual messages that are working its way through the network. How'd we do based off the initial set of goals that we wanted for this solution? We're still not there on our sub-second failover. We would like to get there. We're still working on it. We know we can do BFD and fast reroute. We've recently migrated to NoviFlow for switches, and they have some features we want to implement inside that will help us get to that level. We still are working on correlation engines. So how do we take more and more data points in to build up what the final state of the network is? And there's some new features that we've been asking from NoviFlow that we want to start to implement. For example, having the switches put a timestamp on every single packet as it goes through the network so we can get real latency data on a hop-by-hop basis through the network. What's next for us? The biggest one is putting a GUI in front of this. We are, like I said, releasing this back in the open source world. It works, but TPN has its own GUI, its own admin interface. We don't need a pretty interface on top of this. We can do everything through the northbound API. So we want to come back and put a decent interface in front of this. We want to continue to expand functionality. Those correlation pieces we will be working on forever. I think that's the real heart of this system. What we were trying to do when we set out with this was actually build a system that allowed us to take in, like I said, millions of data points a second and make a decision on what the network looks like. And for the development team right now, it takes us, the joke is it's a 2-beer compile. So by the time you say go compile, you can finish 2 beers before it's actually done. I'd like to get it more to 3 or 4 beers, but the rest of the team would like to get it a bit faster. So we're looking at making some changes to the build environment. It does build everything in Docker. You can spin it up on your laptop. Your laptop will then take off like an airplane. In production, we run this across Horton DataWorks platform inside the core of our network, so it has a little better scale. So last slide, we really do want to get involvement on this. My boss has given me a KPI on the number of people that fork and clone and interact with GitHub, so your homework is to go and clone and fork this thing right now, please. But we really do want to bring input in and start to get some input back on what it does. It's fairly easy build environment, it is a 2-beer operation at the moment to build it. And there is a vagrant-based Unix environment, so you can spin the thing up and not have to have all of the libraries and everything directly on your local build environment. Thank you.